Lewis theory, in combination with valence shell electron pair repulsion theory, or VSEPR theory, can be used to help predict the shapes of molecules. VSEPR theory is based on the idea that electron groups, lone pairs, single bonds, or multiple bonds are going to repel each other. This repulsion between the negative charges of the electron groups on the central atom ultimately determines the geometry of the molecule. So if we wanted to predict the shape of carbon dioxide, which has the Lewis structure of oxygen double bonded to carbon double bonded to oxygen, the geometry of this CO2 is going to be determined by the repulsion between the two electron groups, or the two double bonds, on the central carbon atom. These two electron groups get as far away from each other as possible. This is going to result in a bond angle of 180 degrees in a linear geometry for carbon dioxide. Next, we're going to look at the shape of carbonic acid. Carbonic acid has a Lewis structure of a central carbon atom double bonded to an oxygen and two hydrogens on either side. This molecule has 3 electron groups around the central atom. We have a cluster of electrons here, cluster of electrons here, and here. These 3 electron groups are going to get as far away from each other as possible. This is going to result in a bond of 120 degrees, or something we call trigonal planar geometry. These angles that have been predicted for carbonic acid are approximate. The double bond contains more electron density than the 2 single bonds. This results in a slightly greater repulsion, thus the HCH bond angles are actually closer to about 120 degrees. If a molecule has 4 electron groups around the central atom, like methane, it's going to have a tetrahedral geometry with bond angles of 109 degrees. Here we have both the ball and stick model and then also the space filling model for methane. Space filling models more closely portray those molecules. Ball and stick models are often used because they kind of clearly illustrate that molecular geometries. The mutual repulsion of the 4 electron groups causes this tetrahedral shape. This tetrahedral shape allows for maximum separation among the 4 groups. When written on paper, it seems like the molecule should be square planar from the skeletal structure with bond angles of 90 degrees. However, if we move out into 3 dimensions, the atoms can actually get even further apart with that tetrahedral structure and get closer to 109.5 degrees. The ammonia molecule has 4 electron groups, 1 lone pair, and 3 bonding pairs of electrons. If we look only at the electrons, the electron geometry, the geometric arrangement of those electron groups, is tetrahedral. The molecular geometry, the geometrical arrangement of the atoms, is going to be what we refer to as trigonal pyramidal. The lone pair exerts its influence on the bonding pairs, but there's no atom attached to it, so you don't quite see it. The bond angles of the ammonium are actually a few degrees smaller than the ideal tetrahedral angles. However, it's got that general tetrahedral shape. We're just missing an additional atom attached to the top. If a molecule, the water molecule, the H2O molecule, has 4 electron pairs and 2 bonding pairs. If we only look at the electrons in the electron geometry, the geometrical arrangement of the electron groups is tetrahedral. We have 4 groups of electrons. The molecular geometry, or the geometric arrangement of the atoms, is actually what we call bent. The lone pairs are going to exert their influence on the bonding pairs, causing this bent structure where we don't have a totally flat or planar structure. So, to kind of summarize predicting the shapes of molecules, if there's 2 electron groups and 2 bonding groups and no lone pairs, we are going to get a linear geometry. if there's 3 electron groups, 3 bonding groups, and no lone pairs, we're going to end up with trigonal planar geometry, where we're flat and sort of triangular. If we have, excuse me, if we have 3 electron groups and 2 bonding groups and a lone pair of electrons, the electron geometry is going to look trigonal planar, but what we are going to actually end up with is a bent design, or a bent arrangement of the atoms. If we have 4 electron groups, 4 bonding groups, and no lone pairs, we get a tetrahedral. If we have 4 electron groups, 3 of them are bonding and 1 of them is lone pair, we have a trigonal pyramidal. And then if we have 4 electron groups, 2 bonding groups, and 2 pairs, we're going to end up with a bent configuration as well. So, to sort of summarize, if we are going to predict geometry using that VSEPR theory, we want to first draw the correct Lewis structure for the molecule. Once we have drawn the correct Lewis structure for the molecule, we're going to determine the total number of electron groups around that central atom. Once we do that, we can determine the number of bonding groups and the number of lone pairs around that central atom. And then you can refer back to table 10.1 to help determine the electron geometry and the molecular geometry. So we have an example that we can work out where we are predicting the electron and molecular geometry of phosphorus chloride. Take a few minutes, try and work through this on your own, and then if you have questions, feel free to play the video and double check your work. So we're going to start off by drawing the Lewis structure for this molecule. Phosphorus chloride is going to have 26 electrons. If we go back to our periodic table, we will see that our chlorine atom has 7 valence electrons and our phosphorus has 5 valence electrons. So we're going to need to place those all around. We want to ensure that we put 2 electrons in between, or a pair of bonding electrons in between the chlorine and the phosphorus, the chlorine and the phosphorus, the chlorine and the phosphorus. Since each chlorine atom only needs to pick up 1 additional electron, and phosphorus has 5, it needs 8, it needs to pick up 3 additional electrons. It's going to pick those up by bonding with and sharing those electrons with 3 individual chlorine atoms. So we're going to determine the total number of electron groups around that central atom. Lone pairs, single bonds, double bonds, triple bonds, each one of those are all going to count as a single group. So the central atom has 1, 2, 3 electron groups. 1, 2, 3, 4 electron groups around it. It's got 1, 2, 3 single bonds and 1 lone pair of electrons. So determining the number of bonding groups and the number of lone pairs around the central atom, the sum should result to, these should sum to the result from step 2. Bonding groups include single bonds, double bonds, and triple bonds. We also have a lone pair of electrons right here. So if we go back to our table 1, we're going to look at our electron groups. We know that we have 4 electron groups. We have 3 of them are bonding and 1 lone pair of electrons. This is going to give us an electron geometry that is tetrahedral, but the molecular geometry is going to be trigonal pyramidal because we have that lone bonding pair up here. That's going to push all of these others down and out, and this is going to give us our trigonal pyramidal molecular geometry. Here is another example where we're going to predict the electron and molecular geometry of the nitrate ions. So you start off by drawing that Lewis structure for the molecule. The nitrate ion has 24 electrons. We're going to spread them all around. We're going to see that in our nitrate ion, we have 1 bonding pair between oxygen and nitrogen. 1 bonding pair between this oxygen and nitrogen. And then to fully satisfy our nitrogen, as well as our oxygen, we're going to need an additional bonding pair between this nitrogen and this oxygen. So we're going to have 2 bonding pairs. This is going to leave us with a double bond. So now we need to determine the total number of electron groups around the central atom. Lone pairs, single bonds, double bonds, and triple bonds all count as a single group. So we have 1, 2, 3 electron groups around this nitrogen. The central atom has 3 electron groups around it, reminding you that that double bond only counts as 1. So once we've determined the number of bonding groups and the number of lone pairs around the central atom, we see that we have no lone pairs around the central atom, so we're left with just 3 bonding groups. If we go over to our table, we'll see that we have 3 electron groups and we have 3 bonding groups and no lone pairs. This is going to leave us with a trigonal planar geometry. All right, so that is predicting geometry using that VSEPR theory. Please let me know if you have any questions, comments, or concerns. I'd be happy to go over anything with you.